what you expect. Okay, so here, maybe one here. Okay, your uniform. Okay, one more peg over here. Give yourself. Okay, I just passed you what is called a heat pack or a hand warmer. For those of you that may have been to a cold country and your jackets are not enough, sometimes you may have bought these packets. Okay, right now, if you look at these packets, they are sealed tight. They are airtight at the moment. Okay, nothing can go in. Okay, but this is what I want you to do. Okay, you can read the instructions behind. You can read the instructions behind on how this works. You can read the ingredients of each pack. Okay, what ingredients do you see? Iron, right? You see iron? So actually there's metal in there. Anything else you see? That's water. How about water? Water. Oh, okay, cool. Here you got water. Okay, so you see some iron powder, you see some water. Okay, so how does this work? What the instructions say? Okay, once you're done reading, you can pass to another pair if they've not read yet. Okay. Alright, what does the instruction say? It says that for it to work, you need to tear this pack open. Okay? I'll let you now tear the pack open. Okay, tear open. Okay, once you tear it open, I'd like you to leave it at your table. If you want to, you can give it a shake. Then you can hear the powder inside. You hear the iron powder inside? You can give it a shake if you want to. You can get a powder. In a while, something quite special is going to happen. When I went to a cold country, I did the most stupid thing. Okay, so it's actually a sticker. If you want to, you can actually remove the sticker, then you can paste it on the surface. Right? I did the worst thing ever. Yeah, I was really cold, so I pasted it on my skin. Yeah. And then at the end of the day, when I removed this sticker, right, a layer of my skin came off along with it. Why though? The layer of skin came off because this pack over here, in a moment's time, will start to get really, really, really hot. I underestimated how hot it can get. So I actually got a burn on my skin, and when I peeled it off, one layer of skin just came off. It was the most painful experience ever. But I felt so warm the entire time. So in a while, you start to feel it get warm. In fact, if you start to feel it now, it's starting to get warm. Yeah, can you feel it? Getting warm? No? Then you gotta shake it off. Yeah. You know what that say? You don't got shake your price before now. Okay, I don't go. Getting warmer? Yeah? Okay, in a while, right, it will get really hot. Like really hot. Oh, why did I tear? Sorry, I give you back. Yeah? I'm going to show you a video now of how this pack works, because it relates quite closely to where the chapter we're going to go into next.
On freezing winter days, a pocket-sized hand warmer can be a lifesaver. Office worker Chontina always carries it on her way to work. Keeping a hand warmer in a pocket helps her get through the cool weather.
Anyone here speaks Korean? No? Who? Shannon speaks Korean. Okay, Korean. Sorry, not Korean. Shannon, you translate. I called Shannon Korean.
흔들기만 해도 금방 따뜻해지더라고요. 거죠?
To find out what's inside the packet, we opened it up. It contained powder, but what kind of powder is it?
가벼운 핫팩에는 철가루가 있고 소금이나 활성탄 등이 들어가 있습니다. 기본적으로 철은 산화라는 과정을 거치게 되면 열을 발생시키게 됩니다.
But in everyday life, it's hard to notice iron releasing heat as it forms rust. Then, how do hand warmers use an oxidation process to generate heat?
철가루가 되면 표면적이 급격하게 늘어나게 됩니다. 공기와 반응할 수 있는 면적이 급격하게 늘어나기 때문에 산화가 더 빨리 일어날 수가 있게 되는 것입니다. 하지만 이것만으로도 충분하지 않기 때문에 그 주변에 촉매작용을 할 수 있는 촉매제, 여기서는 활성탄과 소금 같은 것이 존재하게 되면 훨씬 더 이런 산화작용을 빨리 일으킬 수가 있게 됩니다.
As the greater surface area of a substance can accelerate the chemical reaction, iron is placed in the pouch in the form of a fine powder to produce heat. A lot of people shake hand warmers packets to warm them up, but they can work even without shaking.
일회용 핫팩은 냉동되어 있는 그 포장지를 뜯어내는 공기중에 노출되면서 그때부터 열이 발생됩니다. 그래서 우리가 소자들도 좀 힘들기도 하는데 간단히 도움을 줄 수 있지만 뜯어놓은 그 자체로 열이 발생합니다. 이 열을 차단하는 핫팩의 작용이 멈춥니다. 예를 들어서 만약에 우리가 한 3시간 정도 핫팩을 사용하고 지속시간이 12시간짜리를 밀봉해서 보관하면 다음에 조금 더 쓸 수 있습니다.
The performance of hand warmers usually depends on the level of heat and the length of time it lasts. How do hand warmers maintain a constant temperature and heating time?
핫팩의 성능과 온도를 정리해
Okay, this pack is pretty hot already. Okay, it takes a while. It takes a while. The more you expose it to air, the hotter and hotter you'll get. Mine was so hot until it burned my skin off. Okay, do not try that at home lah. You can try to heat up other stuff you want to. Like you can stick it to your water bottle, then you get a warm drink. Okay, but don't mix it on your skin, yeah. All right. How does this work? Okay, it works through a chemical reaction that I think you have not learned before. Oh, you learned it? Wow, that's my soul. Okay, you all learned it. Okay. So, no, normally when we teach this subject, this particular topic, right, you have not learned this part yet, and then I have to go through the chemistry of it. So you know what redox reactions are. Wow, bless. Okay. I was going to this morning, right? Wow, there's such a smoke here already. I cannot fake my way through. Okay, so you know what redox reactions are, right? Okay. Oh, very good. I can speak in chemistry terms. Okay, so how would you define a redox reaction? What?
One chemical entity in the reaction brings electrons.
Okay.
The other one loses energy.
Okay, so one definition of being oxidized or being reduced is to gain or lose electrons, right? Other than that, who's your chem teacher? Oh, Mr. Low, hey, my best friend, okay. We always come in a pair. Hey, really, we always come in a pair. Yeah, okay, so what are the definitions of redox reactions, you know? Yes? Of oxygen, right? You could gain or lose oxygen. Any other definitions? Of hydrogen, right? Okay, for this particular chapter, we're going to look at redox reactions through the lens of electrons. Okay? What you just experienced there is actually a redox reaction. Okay? And more specifically, iron is the one that contains that electron you want to work with. Okay? After oxidation, okay, when something is oxidized, it loses an electron, right? When something gets reduced, it gains an electron, right? So here, my oxygen. Okay, so if I were to draw this out, number one. Okay, what is number one? Okay, next, what is number two? Okay, get a quick buzz, or you can. Okay, so which one is reduced? Number one or number two? Number two, Number two is being reduced. Oxygen is reduced. Okay, reduction. Right, and then on top, oxidation. Okay, there is a transfer of electrons from iron all the way to water over here. Okay? Okay? So that's the reaction that you are encountering in that pack. And the reaction will continue and continue because the moment you open that pack, you expose the iron inside to the oxygen around you. And you are feeling that heat radiate off that pack, right? That is a form of energy. The question here is, do we harness the energy that's being released from the transfer of electrons? But actually, that's what our mitochondria are doing. Our mitochondria is harnessing the energy that's released through the transfer of electrons. Here, electrons are being transferred from one entity to another. But through the transfer, you also get some release of energy. In your case, in the form of heat. But in our case, in our body, we are going to try to tap on the energy, make something useful. When you're very young, you learn something about mitochondria, right? Does this structure look familiar to you? Do you all learn the structure of mitochondria? I don't think so. Have
Not very.
You're not in depth, right? Okay, what does mitochondria produce? Okay, you all learned that at least, right? Okay, you always say mitochondria is the powerhouse of the cell, right? Okay, you cannot stop saying that. Okay, you all have grown beyond that point. Okay, it's very cute when a primary school student say, like, what's the function of mitochondria? They're like, okay, so you all stop doing that. Okay, so now we have reached a point where I hope you can describe it as such. Mitochondria synthesizes ATP. It is you often see people describe it as the currency for energy in the cell. They call it a currency for energy because a lot of chemical reactions require ATP as a chemical. Okay, a lot of chemical reactions require ATP as a chemical for it to start. Right, that's why they say it's an energy for a currency for energy. Okay. In this chapter on cellular respiration, our key goal is to understand how the mitochondria synthesizes ATP, the currency for energy. But how it synthesizes ATP is actually quite related to what you are feeling at the pack. Rather than let the energy escape into the environment in the form of heat energy, our mitochondria is able to capture the energy that's being released instead to synthesize ATP. Yeah? Okay? So that's what we're going to look at today. And rather than iron, we don't eat iron, right? Okay? Instead, we make use of glucose. Okay? It is the same. Actually, what's happening in your mitochondria is simply a redox reaction. It's just a rather complicated one. Okay? So what you get at the end of the day is oxidized glucose. But more specifically, you actually know what this oxidized glucose is. It's the thing you breathe out. Yeah, it's actually CO2. So if I were to remove this, okay, so I'm just simplifying all this. Mitochondria, essentially what it's doing is just doing what is happening in that pack, just with glucose and oxygen in the air. Okay? And our mitochondria is pretty good. It doesn't just let the energy escape into the environment. You don't become a very hot being when you eat glucose, right? Instead, it uses the energy to produce this. Okay, that's what we're going to find out today. Okay, so this is the notes for today. Yeah, just covered the first part. Okay, if you want to spend some time taking down some notes, you can do so. But I'm going to set up the whiteboard again. Next, we're going to understand what exactly the mitochondria looks like on the inside. Okay. I'm going to erase. If you want to take a photo, you can take a photo and take a note. Good. Okay. Okay, so the question is how? How does our body, or mitochondria specifically, create ATP? To understand how, we must first understand the structure of the mitochondria first. How many phospholipid bilayers do you see here? Two are, Ken? How many layers of phospholipids? Okay, so we just practice. Okay, so there are two layers of phospholipids here, each one corresponding to one layer of the mitochondria. Okay, first and foremost, mitochondria has two layers of membranes. Okay, there is the outer membrane, and then there is the inner membrane. Okay, so that's the first thing to know. You learned this before in lower J? Remember? Yes. Never? Okay. It will mean not complicated also, outer and inner membrane. Okay? You want to make an educated guess what this space in the middle is called? This space between the membranes. Cytoplasm? It's not cytoplasm. It's the intermembrane space. Yeah, for once it's not out of this volume. Intermembrane space. Okay. Next, you see this inner space over here. Yeah. The space inside here is called the matrix. You know, watch the latest Matrix movie. Oh, I heard it's real bad. Nobody watch Not your time. Okay, yeah, not your time of movie You want to watch the first Matrix movie? That was pretty good. Okay, so the inside is called a matrix And what's the outside therefore? Is the cytoplasm. Okay, that's where the mitochondria is floating in. Okay. Okay, we need to know the various structures and the spaces because where these redox reactions take place, they take place in these spaces. So we need to know where. Okay. For today, we're just going to look at the first few redox reactions that take place to help you get as much energy as possible. Okay, you take your time to draw this in now. Okay, some more vocab for this chapter before we move on. First, for every redox reaction, there is an electron donor. What is it for? Maybe chemistry don't use it. Okay, so there's an electron donor, and then for redox reaction, there will also be an electron acceptor. Okay, so I just want to introduce these terms to you. Here we have a donor, okay, an electron donor. Then we also have an electron acceptor. Okay, so some terms for you, some vocab. Okay, last vocab for today, so that we can understand the subsequent processes. Okay, other than electron donor, electron acceptor, you have downloaded the notes, right? Okay, bye-bye. Last word we're going to look at today, electron carrier. Okay. What's the role of electron carrier? Okay, in truth, if glucose were to give up all its electrons to oxygen at one go, it's going to be a very, very explosive reaction. Right? Lots of energy will be released at one go. And that's not something that our mitochondria can handle. Instead, we break down the steps into many, many, many short steps so that we can grab the energy so that we can grab the electrons bit by bit. Okay? So, along the way, you will later on see that rather than transfer it directly to the electron acceptor, we actually have things called electron carriers. Okay, that help to shuttle the electrons eventually to oxygen. Okay, if we just transfer electrons all at one shot to oxygen, actually it's quite devastating. Okay, so there is an intermediary that will help to shuttle the electrons over to oxygen. That's what we're going to focus on today. Okay, and you will come across this word very often. Okay, you will see this very often. NAD+. NAD+ is the electron carrier that you'll see very often today. Okay? You've actually encountered NAD+ somewhere in a textbook in JH3. It is actually a biomolecule. More specifically, it is a nucleo. It is a form of nucleotide. Okay, with that, I think we are ready for today. So if someone were to ask you what are the functions of nucleic acids, other than storing genetic information, it can also be part of shuttling electrons from one place to another. Okay, we are ready for today. For those that are ready, I'd like you to go to SLS. If you go to the chapter on energetic cellular respiration, go to A first. Okay, after you completed A, then we'll move on to B. Okay, so for those that are ready with your notes, I'd like you to go to A first. Okay, I'd like you to key in as many things as you think that is needed for cellular respiration, and then we will see where all these things come into play. Right? As a primary school student, you know that cellular respiration is the thing that uses oxygen, uses glucose, produces carbon dioxide. But at the end of this chapter, you will know exactly where it's used, exactly where carbon dioxide is produced. Okay, so what is needed? Right, you need food. Sorry, Nat, can you go to C? It says C without any H. Beyond that. Okay, what is needed? Food. Yes, we do need food, we do need oxygen, we do need glucose. More specifically, we need food in the form of glucose, okay? Okay, so we need glucose, we need oxygen. Anything else? Okay, so then you pay close attention. If we say we need glucose and oxygen, I want you to pay attention where exactly it is used. So, okay, Kila, just like, okay, let's have a look. What is that flying around? This is A. You go on. Oh, okay. Okay, it's just a small little honeybee. So, okay, the most distinct ones. Then you'll die. Okay, so anything else? What else is needed for cellular respiration? Okay, many of you put food and oxygen, glucose and oxygen. Okay, anything new? Okay, enzymes. Okay, see me put enzymes. Indeed, I would like you to pay attention to this whole reaction, redox reaction. A lot of enzymes are being used along the way. Okay, so largely we see glucose, oxygen, food, NAD+. Okay, so we do need electron carriers. Right? So some of the things that you listed down, number one, we need oxygen. Okay, pay attention to where and when oxygen is used. Next, we also need glucose. Want you to pay attention at what stage it's used. We also need NAD+, which is an electron carrier, to help to grab as much electron from glucose as possible. Last but not least, we need enzymes. Very sharp. Yeah? We do need enzymes. Most reactions in our body need enzymes. Okay, now we're going to skip to section C today. Okay, we're going to go to section C. We'll come back to B tomorrow. Oh, what did I do? Okay, we are 407. Okay, let's go to section C. Oh, I paused it. I always do this thing. Okay. Okay, let's go to section C. In your SLS, whatever is we are going through in section C is the correct sequence of things. Okay. In your textbook, on the first few pages, you will see something like that. Okay. These are the stages of cellular respiration that we're going to understand. You see that there are 4 stages: glycolysis, pyruvate oxidation, citric acid cycle, and oxidative phosphorylation. Okay? Section C is what we're doing today. We are going to go through this, this, this. And then we'll take a break. Tomorrow when I see you, this is what we're going to do in the very last stage, which is in the part B. Okay. But actually, this part I'd like you to try it yourself. We're going to find out what are the various reactants and products of each stage. Okay? And that's the focus I want you to focus on. This particular chapter, I want you to put on the lens of interactions. Okay? Just like the previous chapter on genetic expression interactions. So, when we look at interactions, several questions come in mind. Where is this interaction taking place? Who is involved? And why? Or rather, what is produced? Okay? Your goal for this morning is I'm going to get you to read the first 3 stages. Each stage only, I think, takes up 1 page, not even a full page. Your task is to highlight and tease out who is involved. Okay, what is needed for the interaction? What is produced in the interaction? Right? And then we will go through this in a while. Okay, so if you go to part 1, first one, glycolysis. Okay. First segment, what is the change? Okay, what was the before, what was the after? Second, what is needed? And we will repeat this for the first few segments. Okay, so just like you complete tab 1 and tab 2 for this morning, and then we'll run through in a while. Tab 1 and tab 2. In order to do this, you need to read your notes along the way. I'd like to give everyone around 12 minutes to accomplish this task. Then we'll go through as a class. You may discuss with your friends, yeah? What is needed, what is produced. 40 more seconds and we'll go through tab 1. Okay, you need to take a break. Okay, we're going to go through tab 1 first. Tab 2 can be your homework for today before we come into lesson tomorrow. Okay? Alright, let's look at tab 1. For those that are ready, you can go to tab 1. You can view your friend's submissions, have a read of what they've input. Okay, what is the change? Okay, during glycolysis. Okay, what is the change? Okay, let's look at some responses. First, let's look at butane. Each glucose molecule produces a net number of 2 ATP molecules, 2 molecules of pyruvate, and 2 molecules of NADH. Was this what you captured? Okay, largely, right? Okay. Do you understand what it means by net of 2 ATP? It uses 2 ATP at the start just to kickstart the reaction. You know how when you burn things, it's actually an oxidation reaction, right? Just a little spark of energy can kickstart the whole process. We also need a little bit of ATP at the start. We produce 4 at the end, so it's a net of 2. Okay, so that's what it means, huh? Okay, let's look at other responses. Let's look at Sanjeev's. 2 molecules of pyruvate, 4 molecules of ATP is produced from a single glucose molecule. Okay, and then but where did the energy come from? It came from the 2 ATP at the start. So the same idea of a net of 2 ATP. Okay, other than that, 2 molecules of NADH are also formed. Okay, notice that NADH is the thing that is often formed, and everyone is saying that, right? You say that NADH is a product. Look at Ivan's one. He also mentions NADH is also a product. So I want you to take note of this. When NADH is formed, it signifies that an electron has been taken from the molecule. Okay? So here I have NAD plus. When NAD plus gains an electron as an electron carrier, it becomes NADH. Okay? When NAD plus gains an electron, it becomes NADH. So please take note of that. Okay? You may want to write this down somewhere. When NAD plus gains an electron, it becomes NADH. It is now carrying an electron. So let's look at the where, the who, and the what is produced. Okay, let's synthesize what everyone has written. The where. Where does glycolysis take place? The cytosol, yeah? It actually does not take place in the mitochondria. So first thing to take note, glycolysis takes place in the cytoplasm. Okay? The word glyco means sugar, lysis means to break. Okay? What is involved? Glucose, as everyone mentioned, is converted essentially to pyruvate, specifically to pyruvate. Other than that, you also gain a net of 2 ATP. Other than that, you also mentioned that you gain NADH, right? Okay, so whenever you see NADH, it means that electrons have been extracted out. Okay? Maybe a bit clearer. anytime you see NADH means electrons have been extracted out. If you want to draw the reaction out, it looks something like that. So NAD plus, once it gains the electrons, becomes NADH. Remember, these are our carriers. If we want to grab all the electrons at one go, we want to slowly grab it. Okay, so that's the skill we need to pick up for this chapter. We must be able to know when. Where is the reaction taking place? Number 2, who is involved? Number 3, what are the products? Okay, then you have clearly identified the key products at the end of this reaction. The where, the who, and the products. Okay, that's very important when we look at interactions. For today's homework, I'd like you to work on tab 2 if you have not completed, to spot what are the where, the who, and what is produced for each stage also. Tomorrow we'll go through remaining 2. Link reaction, or as is written inside your textbook, pyruvate, pyruvate oxidation. Okay. And then we'll go to number 3, which is the citric acid cycle, or also known as the Krebs cycle. Okay. Your task is to find out the 3 above, the where, the who, and the what is produced. If you've already done so, then you don't have anything to do for today. Okay? Then tomorrow, we are going to just complete 2 and 3, and then we'll break out into groups and we'll do a quick skit role playing for the very last part of oxidative phosphorylation. Okay? I'd like you to take some time now, touch up your notes, or you finish off the tab 2, and tomorrow will be the more hardcore fun lesson. Notice the packs aren't getting very hot. Maybe only works better in the cold weather. What are you saying? Maybe because it's Daiso. Still warm though. It's a bit warm. I cannot tell if it's warm because of the body temperature. Okay, so finish off the last step. Now slowly tear down the back. Okay, so some homework for today. Number 1, SLS tab 2. Okay, number 2, to prepare for tomorrow also, can you read up oxidative phosphorylation? Just a short paragraph. I think it's less than 10 lines. Okay. Okay, that's all for today. You want to go for a color break? Yeah? Okay, you can go for a short break, or you can continue on tab 2. Or if you have any questions, I'll be happy to go around and answer. Do tab 2, read up on oxidative phosphorylation for your textbook. It's just a short, just one page, I think.